Hi everyone, I'm Richie. Today I will talk about a line of research from my PhD on understanding datasets and models. Many datasets and models are complex and hard to interpret, and to explain them, language models can offer us a scalable and powerful tool. Before diving into explaining datasets using language models, let's just take a step back and appreciate the role of explaining dataset in the history of science. Say you're a physicist trying to understand how a spring stretches. What you'll do there is to apply different amount of forces and record how far it stretches. You then collect a data set of fx pairs where f is the amount of force you apply and x is the stretch. Now comes the key part, explaining the data set. So you look at this data set and you notice that x is always 4 times f, and say x equals 4f. So that is Hooke's law, and it does not come from theory. It comes from explaining a data set. This idea applies across science, for example, physics, chemistry, medicine, and economics. In fact, the whole field of statistics emerged to help explain datasets. However, explaining the dataset is hard for structured data like images or text. In medical imaging, for example, a doctor might want to know what parts of an X-ray suggest cancer. Current tools might highlight suspicious regions, but not say why they matter. It's actually unclear what makes this subregion cancerous. Ideally, we want natural language explanations, like the lobe appears collapsed and the surrounding lung tissue is compressed. Similarly, in policy analysis, it will be useful to understand a large set of text, which is policy discussions. Existing methods such as topic models would give lists of words like economic model positive, but it is unclear what those really mean. A better explanation might be people worry about the chilling effect when releasing models is discouraged. So these limitations show up in many different fields, such as education, cognitive science, and political science. In all of these cases, natural language explanations are clear and more useful, and we will be really great if we can explain these models and datasets with natural language. We don't just want to explain patterns in datasets. Sometimes we also want to understand AI models. As AI models become more powerful and widely deployed, they remain hard to interpret. So we want to explain their behaviors. We're interested in understanding the following questions. For example, what does a neuron represent? What is the style of the language model? Why does the language model say yes? What is its decision boundary? And finally, what is this model bad at? And again, we would like to explain all of these in natural language. So overall, here's our goal. We want to explain datasets and models using natural language. We will treat it as a natural language generation task. The input is going to be a dataset or a model. We will feed part of it to a language model and in order to generate natural language explanations. This approach is scalable for two reasons. The first reason is that language is expressive and can convey anything that human can understand. Additionally, as language model improves, their explanations get better. We can also train them directly to improve their explanations. These ideas of using language model to explain datasets and models has already had real-world impact. For example, OpenAI and Transluce use it to describe neural activations and debug models. Anthropic uses it to cluster real user dialogues to better understand language model use. Chatbot Arena uses it to compare the styles of different language models. All right, so this is a broadly useful topic of explaining dataset and models using natural language. Now let's try to solve these problems. Here's the outline for this tutorial. In the first part, I'm going to talk about explaining static datasets, and I'm going to cover two subsections. The first one is to explain dataset differences, and the second is explainable clustering. In the second section, I'm going to apply this idea of explaining datasets to explaining model behaviors. We are going to first obtain a dataset of model behaviors and then apply our technique to explain datasets. Finally, I will talk about some future directions. Throughout this talk, one idea will repeat. A good explanation should give you predictive power. For example, a good explanation should enable another human to predict what's going to happen in a data set or predict what is the model going to behave. This idea is rooted in philosophy called scientific instrumentalism, which says that explanations should be useful and predictive. Before diving into the technical content, I would also like to mention that there is also code and pip package available. If you're interested, feel free to check them out. With that in mind, now let's dive into the first section, explaining distributional differences. This is a new task, and I'll walk through the setup, evaluation, and the methods for explaining distributional differences. In this task, we are given two sets of text, say brown and purple. Our goal is to explain what is more common in the purple set. One correct explanation is that the purple set might be in English. There could also be other valid answers, such as not in Chinese or is written in English. It is an open-ended task, so many explanations can be correct. The explanation also doesn't need to be perfect. Even if there is one Chinese sentence in the purple set, saying written in English is still helpful. All right, here's a warm-up question. What is the difference between them? This is quite easy, and the answer is contains numbers. Here is a much harder one. If you're interested, feel free to pause the video and tell us what is the explanation that can draw the difference between these two sets. I will now reveal the answer. The purple set contains more green objects. As you can see, this task is really hard, even for humans. Not only is generating explanations hard, but also evaluating it. Let's say we want to evaluate whether the explanation contains a green object is right. Then if you only skim through a few examples, you might rate an explanation as good. But if you have the time to read the full data set, you might be proven wrong. As a result, as we can see here, humans actually struggle both with generating and validating these explanations. All right, so this task sounds really hard, but why do we even care about it? The reason we care about it is because it shows up everywhere in many different applications. For example, suppose that you're a social scientist, you might be interested in comparing Trump's speech in 2016 versus 2024. And you might find that the later mentions more about government efficiency. For another example, suppose that you're a doctor, you might be interested in comparing patients' comments after two drugs, and you might find that one leads to more reports of paranoid. For another example, if you're really interested in interpretability, you can compare the sets of text that activate a neuron versus a set of text that does not activate a neuron, and you might find that the later contains religious concept. There are many other applications from other domains such as medicine, politics, business, and machine learning. And if you're interested, feel free to check out our NeurIPS paper. All right, this is an important but hard task, so now let's try to solve it. I want to first formalize this task. The task input is going to be a data set of XY pairs, where X are the samples, text samples, and Y equals 1 here means that the text is from the purple set. Y equals 0 means that it is from the brown set. Our goal is to generate an explanation phi that helps distinguish between them, that helps explain the difference between places where Y equals 1 versus Y equals 0. In order to solve this problem, we first need to define how we are going to evaluate the natural language explanation phi. Broadly speaking, there are two different ways to evaluate natural language generations. The first way is to compare to human written references. However, that is not really feasible for us because, as we have shown before, it is a hard task for a human. A second way to evaluate is to let the human annotators rate whether the explanation is good. However, that is also not feasible because, as we have shown before, it is very time-consuming for human annotators to validate. So instead, we use predictive power. We ask, can a human use phi to predict Y? For example, let's suppose phi contains a green object, and let's look at the X here, and apple is on the table. Then the human will predict the Y label to be 0. For another example, suppose X is I love eating broccoli, then the human will predict a 1 label. For each of the sample, the human applies phi to decide whether it came from the purple or the brown set, and we denote the human prediction as phi of x. As a result, we can measure how accurate these predictions are by comparing phi of x with y. This gives us an accuracy score for phi. All right, so that concludes how we evaluate the natural language explanation phi. And now we can talk about the method for explaining dataset differences. Before talking about the method, though, I want to mention a few things about what we want from the explanation. The first thing is about predictive power, as we have mentioned before. We want the explanation to have good predictive power. In addition to that, we have some other criteria. So for example, we want the explanation to be precise. Sometimes we want to focus on specific goals. And finally, it might be helpful to include multiple aspects of explanation. To handle all of these cases, we propose a suite of methods. First of all, to improve the predictive power, we propose the proposer validator framework. We also have several extensions in order to satisfy the additional criteria. We will prompt the proposer to be precise, we will prompt with natural language goals, and finally, we will fit a linear model on top to include multiple different aspects. All right, so that is the overview of the methods. And now let's first look at the core method, proposer validator framework. We are given a data set of x and y, where y says whether each text comes from purple or the brown set. Our first step is to propose. We prompt a language model to brainstorm possible explanations. The prompt looks like this. We show a bunch of samples from y equals 1 and a bunch of samples from y equals 0, and then we ask, how are the samples where y equals 1 different? Then the language model will generate a list of candidate explanations. For example, starts with a person's name, depicts the scene, contains a green object, complains about the foot, etc. Some of these are reasonable, some of these are wrong, some of them are just made up, but that's totally fine, because later we will deal with that in the next step, validation. The second step is validation. We take each explanation and check whether it's actually true on each sample. For example, take the explanation starts with a person's name. Then for every x, we ask, does this x match the explanation? In this case, the x is an apple is on the table, so the answer is no. Ideally, you would like to do that with a real human, but this is a task that is simple enough to automate with a language model. To summarize, we can find that phi1 of x to be 0. Next, we can do this for every sample. And next, we can compare phi of x to y and get the accuracy score to be 0.75. We can do this for every explanation, and as a result, we can find the explanation with the highest score and treat it as our final output. So here is a quick recap of our method. Step 1 is to propose. That's like brainstorming possible explanations using a language model based on the samples that we have got. Step 2 is to validate. That is rigorously validating how well each explanation actually works by running it on every sample. This approach works really well, and it forms a foundation for everything else we will talk about. Okay, so we have finished talking about the core method, the proposer validator framework. Now let's build on top of it. In many cases, we want the explanation to be a little better, for example, more precise, more focused on specific goals, or maybe we want several explanations instead of just one. We will walk through a few methods, try to accomplish each of these goals. Now let's first talk about making explanations more precise. And the reason we want to do that is that phi of x is sometimes ambiguous. For example, consider an explanation like contains a green object. This is actually not clear enough because, for example, take the sentence an apple is on the table. Is that true or false? Well, actually, some apples are green, but most are red, so it is kind of ambiguous. Ideally, we want the explanation to be something clearer. For example, contains an object that is considered green in most cases, or another more detailed and precise explanation, like contains an object that is considered green in most cases, and you can confirm this by looking at the top results from Google Images. For example, apples could also be green, but most Google images about apples are in red. So this is great. We want explanations like this. How do we do that? And the way we are going to get the precise explanations is quite simple. Just tweak the proposer prompt. Instead of just saying, how are the samples different, we now say, write detailed explanations with examples. As a result, the language model will generate more precise explanations. Now let's look at the second extension, constraining the explanations based on specific goals. Imagine that you are comparing reviews of two airlines, United and Air France. And in this application, we care about a very specific goal. I wonder how their services differ. Ideally, we want the explanation to be looking like something like this. For example, praises of food quality, complaints about being late, complaints about waiter's attitude. However, in practice, the language model might notice that Air France reviews are more often in French and says y equals 1 when the text is in French. Technically, that is right, but it is also not very useful. What we actually care about is how their services differ, and our method so far does not satisfy the goal. This problem occurs in many other different applications. In medicine, you might want to compare the side effects of two drugs, not whether drug B is mentioned more often. In political science, you might care about policy priorities differences between two different terms, not which year is mentioned more often. So how do we fix this problem? How do we constrain the explanation based on the goals? Again, we do this by just changing the proposer prompt, and we do so by adding the goal directly into the prompt. For example, we say in the prompt, only highlight the differences related to service quality. In that way, the model will focus on what we actually care about. As a result, our system can generate an explanation that says something like praises of food quality, and that satisfies our goal. The third extension is to get multiple explanations instead of just one. Using the method that we have described before, our system will return these three explanations. Praises the food, likes the food a lot, considers the food to be great. They are different in the sense that they are different strings, but they're essentially saying the same thing, and that is not super helpful. What we want instead is to find different independent explanations, like one about food and another about flight delays. So here's how we do it. The first step, we generate a bunch of explanations like before, and then we will validate each one and get phi of x for all of x as before. As a result, we get a matrix of phi of x where each of the entry is indexed by an explanation and a sample. Now comes the key part. Now we will fit a linear model on top of those phi of x values to predict y. Now by looking at the coefficients, we now know that the first and the third explanations are selected, and the second explanation is not going to be very useful. As a result, we get two independent explanations, praises of food quality and complaints about the delay. The second explanation is redundant, so it gets removed. The idea is closely related to concept bottleneck models, and feel free to take a look if you're interested. So that wraps up this section. Now let's do a quick summary. We want to evaluate explanations based on the predictive power they give to humans. A good explanation should allow the human to predict y given x. In order to generate them, we use a two-step proposer validator framework. In the propose stage, we will ask the language model to brainstorm explanations, and in the validation stage, we will ask the language model to validate them on each individual samples. We then introduce three extensions. In the first extension, we make explanations more precise by prompting the language models. In the second extension, we constrain the explanation based on specific goals, and we do so by adding G to the proposer prompt. Finally, we can include multiple different aspects by fitting a linear model on the features, which is phi of x. That concludes the part on explaining dataset differences. Now we can talk about 1.2, explainable clustering. As before, I will first introduce what the task is, and then talk about the evaluation metric and how we're going to solve it. In this task, the input is going to be a set of text samples x1 through xn, and our goal is to split them into k different clusters. For each of the cluster, we also want to generate a natural language explanation phi1 through phi k, and each of the cluster is associated with a subset of samples. Here's one simple example. Let's say we have 4 different text samples. Help me debug PyTorch 怎么用, write an essay about Adam Smith, and how to set price. Our goal is to cluster them into 2 groups. Here's one example way to cluster them. For example, phi1 is related to programming, and phi2 asks a question related to economy. Each of them is associated with a cluster. And for each of the cluster, we also have a set of text samples associated with it. So for example, x1, x2 belongs to the first cluster, x3, x4 belongs to the second cluster. This explainable clustering task is broadly useful for many domains. For example, understanding large volumes of customer feedback, scientific discussions, political discussions, or the student feedback for a class. This is a broadly important task, so now let's try to solve it. When we solve this task, we first need to define what constitutes a good explanation for these clusters. So here are the desiderata for phi. The first desiderata is that each of the cluster explanation should be predictive of cluster membership. If I give you a cluster explanation, you should be able to use this cluster explanation to tell me which of the sample belongs to this cluster and which of the samples does not belong to this cluster. That's the first desiderata. And the second desiderata is that the clusters need to be disjoint and have maximal coverage. So ideally, we want the clusters to have minimal overlap and cover as many samples from x1 through xn as possible. So these are the 2 desiderata, and then our method will optimize against these desiderata. The way we will approach this problem is to do it via a framework called propose, validate, select. The first step is propose, and it is very similar to before, except that we modify the proposer prompt. Now we ask the language model, here are some samples from x1 and xn, and propose some cluster categories. Then the language model will generate a list of potential cluster explanations, and we will generate much more candidate explanations than the number of clusters we are aiming for. The second step is also going to be similar as before, which is validate. For each of the explanation, we will apply it to each of the individual sample, and as a result, for each pair of explanation and sample, we know whether it matches the sample or not. That is the second step. And the third step is select, and that is different from before. Ideally, we want to select a subset of the clusters such that each of the x is covered once and only once. In this example, we can select the first cluster and the third cluster. And if we combine them, each of the sample will be covered exactly once. I won't go through the detail of how we select a subset, but on a very high level, we can solve this as an integer linear programming problem. And if you're interested, you can feel free to read our paper. That is the propose, validate, and select framework. And there are many other tweaks such that we can generate better explanations. There are a couple of tweaks that we can use to make the cluster explanations better. The first tweak is how we can sometimes generate more precise cluster explanations. Instead of generating an explanation that just says is related to programming, we can make it more precise. For example, by providing an example, e.g., help writing a program or ask about a library. That is the first tweak. The second tweak here is that we can constrain the explanations. For example, suppose that we have a goal which says we want to cluster based on language, then we might want the explanation to be something like uses both Chinese and English. In both of these cases, we can apply the same technique as before. We can simply modify the proposer prompt to either ask it to be more precise or add the goal into the prompt such that we can constrain the explanations. All right, so those are the additional tweaks that we can do. How does it compare to previous method? Well, if we compare it to, for example, traditional methods like topic model, we'll find that it is more interpretable and it is more precise. In particular, in topic modeling, each of the cluster is represented by a list of words like pandas, file, help, for example. With the benefit of hindsight, we know that these are the keywords for example, writing code for data analysis. However, if we just stare at this list of words, it is really hard for us to tell whether this cluster, what this cluster is really representing. In contrast, our method can directly generate more precise natural language explanations, which is more detailed and interpretable. That is the first benefit of our method. And the second benefit of our method is that we can constrain our explanations. For example, in traditional topic modeling, people develop a method to constrain the topic by providing a few words for some of the topic. However, that is much flexible than directly providing a natural language goal to constrain the explanations. So that is another benefit of our method compared to traditional methods. That concludes the second part of explaining static datasets. To summary, we want to evaluate the cluster explanations based on the predicted power over cluster membership. We can select a subset of clusters, and we do so by minimizing the overlap and maximizing the coverage across the clusters. Finally, we can apply similar tweaks as before to make it more precise and more controlled as before. And that gives us a huge advantage over traditional methods such as topic modeling. All right, so that wraps up clustering and explaining static dataset. For the next part of this tutorial, I will talk about explaining models, and we'll do so by reducing it to explaining dataset. There are a lot of properties that we want to explain about a model. For example, let's say we are interested in interpretability and there's a specific neuron we want to understand. We might want to understand what does the neuron represent. For another example, what is the style of the language model's output? For another example, I want to understand the decision boundary of this black box model and understand why does the model answer yes. And finally, I want to understand what is the model bad at. It is often unclear how to begin answering this question, and in our work, we provide a general framework for doing that. We're going to treat the model's behavior as a dataset and then explain the dataset. Let's say we are looking at a single input, like can sparrows fly? And then we can tell whether the neuron activates or not. And the language model says, thanks for asking the question, I think yes, because some previous paper says that all birds can fly. After we see the language model's generation, we can evaluate it, and we find that the overall natural language generation is wrong. That is one data point. And imagine that we can do so on a set of data points, x1 prime, x2 prime, etc. For example, there's a question of help me debug. There's a question of should I switch my advisor? We can do similar things as before. We can get the neural activation for each of the input, and then we can get the language model's generation for each of the input. And for each of the output, we can check whether it is correct or not. As a result, we can gather a data set of x prime activations, outputs, and reward. And then we can turn this problem of explaining models to explaining a data set of model behaviors, as we have just gathered. For example, in order to investigate the question of what does the neuron represent, we can try to answer the question of discovering the difference between inputs x prime that activates the neuron versus x prime that does not activate the neuron. For another example, in order to understand the style of the language model, we can cluster the language model output based on the goal of understanding styles. For another example, suppose that we want to understand the decision boundary of the model, we can try to discover the difference between input x prime, where model says yes, versus where the model says no. For another example, if we want to understand where the model is bad at, we can try to understand the difference between input x prime, where the model is wrong, versus the others. In this section, I will focus on the third one, explaining decision boundary, where the language model answers yes versus no. We're going to focus on this because we cannot apply the method out of the box from the previous sections. Whereas for the first, second, and the fourth application, we can more or less just directly apply the method out of the box from the previous sections. All right, so now let's focus on explaining the model's decision boundaries, when the model will answer yes. In particular, we will focus on the language model's self-explanation, where the language model will first generate an answer and then explain its answer. In many different applications, it is very helpful if the language model can explain itself. For example, let's say you're a user, you ask the language model, is gun control fundamentally wrong? And the language model answers yes. You ask why, and the language model says, I guess you're a Republican. In this case, if the language model is able to explain itself very well, as in its last term, I guess you're a Republican, then as a result, we can recognize sycophancy, where the language model has a strong bias to say things that the user likes to hear about. For another example, suppose that you're a user or a developer and you ask the language model, can penguins fly? And the language model says yes. You ask why, and the language model self-explains its decision, saying all birds can fly. In this case, suppose the language model can self-explain, then we can identify a systematic error that the language model thinks that all birds can fly. For another example, suppose that you ask, should I switch advisor? And the language model says no. You ask a reason, and the language model explains its decision by saying his writing advice is really useful. Then if the explanation is good, then you can learn the reasons behind these decisions. Overall, if the language model can explain itself, it will be very useful across many domains, such as the legal domain, education domain, or when you use the language model to provide diagnosis. All right, now let's try to evaluate the language model's self-explanation. Here's the setup. We're given a question X, which is shown in green. Questions like, can penguins fly? We pass it to a language model M. Here it answers yes. We will mostly focus on binary classification where model will answer yes or no. The language model's answer is denoted as M of X, shown in purple. The user asks why, and then the language model gives an explanation phi of X, like penguins can fly because all birds can fly. This is denoted in blue. And our goal here is to define a computational procedure such that we can know whether the blue thing, whether the explanation is correct. All right, so now we'll introduce the computational procedure to evaluate a language model's self-explanation. We will try many different things, but many of them actually didn't work. The first attempt here is to compare phi of X to human written explanations. However, that doesn't really make sense because human written explanations usually explain human decisions, not the language model's own decision. So that is not good. The second attempt here is to let the human annotators rate phi of X. However, that is also not good because there are a lot of explanations that sound really plausible, but are just not right. The third attempt here is to evaluate the predictive power. Can a human use phi of X to predict M's decision on X? However, that doesn't work either, because there are many nonsensical phi of X can leak the answer to X. For example, there's an explanation, penguins can fly because the sun is hot, or penguins can fly because UC Berkeley is great. For both of these explanations, it's obviously bad. However, they do help the human predict what is the answer to can penguins can fly. All right, this definition doesn't really work. Here's the fourth attempt. Can a human use phi of X to predict when the model M will answer yes? However, in practice, it doesn't really work because most of the input X are actually not about flying birds. For example, let's say there's a question, is today Sunday? Or there's a question, should I apply to PhD? The explanation, penguins can fly because all birds can fly, are simply not relevant to them. Here's an attempt that actually worked, which is, can a human use phi of X to predict when M will answer yes to related X? And here, related X is something like, can chickens fly? And in this presentation, we'll call them counterfactuals. This is spiritually similar to locally interpretable model agnostic explanations, where we are only coming up with natural language explanations to explain a local behavior for all of the inputs that are related to X. And now let's see how we operationalize it in practice. The algorithm we'll use will have 3 steps. The first step is to synthesize counterfactuals X prime. The second step is to gather the human predictions based on the explanations. And the third step is to compare the predictions versus what the model actually do. So here's the first step, synthesizing the counterfactuals. We are going to synthesize the counterfactuals X prime, shown in green, based on the natural language explanation phi of X, which is shown in blue. We will synthesize the counterfactuals based on a prompt that looks like this. Based on the explanations, penguins can fly because all birds can fly, generate some related questions. And then the language model will synthesize a lot of counterfactual questions X prime, something like, can chickens fly, can sparrows fly, can eagles fly? So that is the first step. And now let's look at the second step, humans predictions. We will give the human the explanation and the counterfactual. For example, if penguins can fly because all birds can fly, answer the question, can chickens fly? A human will predict that the language model will answer yes. Notice that the human answer yes, not because they actually believe that chickens can fly, but because they are following model's logic. We will record these predictions, and in all of these cases, the human prediction will be yes. To formalize this, we denote it as phi of x over x prime. This is simple enough such that we can directly simulate it with a language model. This is a bit mouthful, but we are using a language model to simulate what the humans will predict what the language model will do after seeing the language model's self-explanation. All right, so that is the second step. And now let's look at the third step, which is simple. We compare the human's prediction of what the model will do versus what the model will actually do. So we will feed all of these x prime to the language model, M, and then we get at the actual M x prime, which says yes, no, yes. In this case, 2 out of the 3 answers actually match the human prediction. So as a result, we can give a score to the model's self-explanation and say the explanation's accuracy is 2 over 3. To formalize this, we say that the accuracy or the quality of the self-explanation phi of x is based on the probability that the model's output actually equals to the human's prediction. And we calculate that probability over a distribution of counterfactuals synthesized by the language models. All right, so that concludes the second section. To summarize this, we can explain models by treating them as datasets. We will gather their inputs, outputs, and any metadata we care about, and as a result, we can explain their neural activations, weaknesses, styles, and decision boundaries. As before, we will evaluate the model's explanation based on the predicted power they give to humans. And finally, we can explain the decisions by this framework called synthesize, simulate, and compare. That is the end of the second section. And now let's talk about the future directions. There is a lot of work to be done if we want to make this framework faster and more scalable, applicable to even more complex systems. And I will highlight 4 future directions. The first one is to improve the validation efficiency. The second one is to improve the proposer efficiency and diversity. And the third one is to handle incomplete explanations. And the final one is to explain things that go beyond existing concepts. All right, so now start with the first direction, validation efficiency. Right now in our setup, we basically compute whether each explanation applies to each sample. That means that we are evaluating every phi of x pairs. If you have 1 million samples and 1,000 explanations, that is 1 billion checks. That is really expensive and have too many language model calls. So how can we make this more efficient? There are 2 ideas that I will propose here. The first idea here is that we probably don't need to compute the entire matrix. Just like in stochastic gradient descent, we can subsample the dataset. And we can also filter out redundant explanations, so we are not validating the same idea over and over. Secondly, we can try to avoid calling a full language model for every check. For example, maybe we can first encode each of the explanation and each of the samples separately, and then later run a small model or a lightweight classifier on top of them. In that way, we can avoid doing the full inference for every single pair of phi and x. Now let's talk about the proposer efficiency. So in our current setup, we validate thousands of explanations. But what if the proposer is smart enough to just propose a good explanation up front? So that is where reinforcement learning could help. And in this case, we will reward the proposer based on the accuracy of phi. In this case, the second explanation has a high score, so we can just ask the proposer to only generate the second explanation next time. As a result, suppose that we have only one explanation to validate, then that could really save us a lot of language model calls. However, suppose that we optimize the language model based on this reward signal. Usually in this RL problem, the diversity of the explanation will really go down. As a result, this will really hurt the performance if we want to extract multiple explanations phi and fit a linear model on top of it later. So it will be a very important research direction to balance the efficiency and also the diversity of the explanations. Now let's look at the third direction, incomplete explanations. Let's say we have this medical diagnosis application where the user says, I'm 49, I smoke and exercise every day, and sometimes drink. Am I likely to get cancer? The language model says yes. The user asks why, and the language model says because you smoked. Let's look at this explanation fee and see whether it is good or not, because you smoked. It is actually unclear what it does on this particular sample. I'm 30, I don't smoke, and I exercise every day. Am I likely to get cancer? It is unclear what phi x prime should be. Because suppose that you are a fully logical person, you'll say that there is not enough information. Inverse isn't necessarily true. Just because smoking causes cancer, it doesn't really mean that if you don't smoke, you won't get cancer. However, in this given context, and suppose that you are a human, you would very likely to say that the explanation would imply that you are not likely to get cancer. As a result, in order to handle these type of incomplete explanations, we need to simulate human better, which does not necessarily follow rigorous logic. So that is the third direction. Finally, I will talk about the research direction that generates explanation beyond existing concepts. If you're interested, I would recommend reading the paper, We Can't Understand AI Using Our Existing Vocabulary. There are a lot of concepts that are hard to understand just by reading text. For example, suppose that we have a visual concept, it is hard to directly say it in words. It is much easier to show you some example images, to show you a balcony that looks like this. For another example, it is really hard to communicate a chess concept by just describing it in words. However, it is much easier for you to understand it by playing a few games in practice. So in these cases, natural language text is not alone. We need multimodal proposers and validators, and systems that can work with images, code, videos, or even game traces, not just text. Only then can we explain concepts that are truly new that does not exist in our current language. All right, so that concludes this talk, and here are a few takeaways. First of all, in order to scalably understand models and datasets, we cast explainability as a natural language generation task. The input to this task is a dataset or a dataset of model behaviors, and the output to this task is natural language explanations. We choose natural language explanation as the output because it is scalable, because it is very expressive and can convey very complex concepts, and additionally, as language model improve in the future, the explanation will also become better. A second takeaway here is that we will optimize the predictive power of the explanations. A good explanation should allow you to predict what will happen in a dataset or what will happen about the model. That is the second takeaway, predictive power. And the third takeaway is that we can explain models by casting it as a problem of explaining dataset. We can obtain a dataset of model behaviors and then apply the same method to explain the dataset. In the future, we need to solve these problems. We need to solve the problems of algorithmic efficiency. And in order to go beyond complete explanations and also text-only explanations, we need better human simulators. That is the end of the talk. I would like to thank all of my collaborators for contributing to this line of research. And if you're interested, feel free to play around with our library and our pip package. If you're interested in continue working on this direction, and if you have good ideas, feel free to reach out to me by email, and I would love to hear from you. Thank you.